Nikola Tesla stands next to his old farmer, who manages his entire farm using a device with stakes driven into the ground. These stakes are connected to an electromagnetic and mainly magnetic field, powering the generators that supply the farm. March 2025. In the basement of New York University stands a wooden box sealed since 1943. It says, Tesla's legacy, high voltage, do not open. The research team is opening it. Inside, wrapped in oilcloth, is a copper coil as tall as a man with hand-wound wire, ceramic insulators, and a brass plaque with the single word, Wardenclyffe. This is a high-frequency resonator, one of Tesla's last transmitters, created in the 1920s. Never cataloged, never mentioned in declassified documents. The team begins measurements. One of the engineers connects a modern spectrometer to the terminals of a coil. The standard procedure is simply to build a resonance curve. The analyzer sends a low-power signal into the circuit. 10 milliwatts. Harmless. The coil reacts, not with a roar, nor a spark, but with a scream. An arch of 2 million volts explodes in the laboratory. Lightning shoots from the coil to a metal shelf 3 meters away. High-voltage sensors installed on the walls trigger instantly. Alarm signals sound on 3 floors. Emergency lights flood the corridor. The evacuation order triggers automatically. 60 people leave the building in 4 minutes. No one is injured, but the resonator continues to pulse, drawing energy from somewhere. The team turns off all automatic switches in the basement. The arch finally quiets down. Silence. Then questions. Hundreds of questions. How can an old device react so sharply? Where did the energy come from? Why did an input of 10 milliwatts lead to a discharge in megavolts? The answer connects modern energy networks, forgotten Tesla patents, and a dangerous truth about resonant circuits. Stay with me. I will show how an antique circuit can cause such a surge today. There is no magic here, only physics, timing, and one bold mistake. This is what makes it dangerous now. Not in 1943, not in the 80s. Today, modern electronics use silicon carbide and gallium nitride, semiconductors with a wide bandgap. They can create tensions that Tesla could only draw on paper. Modern solid-state drivers can excite frequencies up to 10 megahertz with surgical precision. Tesla created his resonators to operate at frequencies around 100 kilohertz. His energy sources were crude. Steam turbines, rotary spark dischargers, noisy and unstable. But the signal generator of 2025 can cover 1 million frequencies in 30 seconds. Automated, controlled by software based on artificial intelligence. The algorithm quickly finds resonance peaks. This is the point of collision. An old coil intended for coarse analog tuning meets modern digital precision. Frequencies coincide by chance, and when resonance is achieved, energy does not flow. It accumulates. Think of a singer shattering a wine glass. The note must perfectly match the glass. Strike it, and the vibrations accumulate until the glass explodes. The coil is that very glass. The signal generator is a voice, and the note was precise. As the command analyzer passed the natural frequency of the resonator, the circuit locked. Energy began to amplify. Each cycle added more tension. The coil rose from milliwatts to megawatts in fractions of a second. This coincidence triggered a powerful discharge. Imagine a sequence of events, the most plausible. No hidden energy sources, no ghostly energy, just poor synchronization. The technician sets up a spectrometer on a metal card, 1 meter away from the resonator. The device begins automatic frequency calibration, low power, standard laboratory procedure. The output wire of the analyzer is positioned too close to the primary coil. Inductive coupling activates. The resonator captures the signal. The tuning passes through 700 kilohertz, right at the center of the coil's tuning range. The circuit activates. The voltage doubles every microsecond. Feedback is generated. The resonator extracts energy from the analyzer, the electrical grid, and radio wave noise. All this is directed to the secondary coil. High-voltage discharge sensors on the ceiling detect ionization. Ozone fills the room. The security system is triggered. Strobes flash. The evacuation alarm sounds. The team has 60 seconds to leave the premises. They manage to do it in 40 seconds. The automatic switches activate, the discharge disappears. But there is a second part. Grounding. If this coil was connected to the grounding network, then the surge of energy received support. This changes everything. Tesla was not just creating coils, he was building systems. His resonators used the Earth itself as part of the circuit, not in a figurative sense, but literally. In 1999, in Colorado Springs, Tesla drove a copper rod 200 feet into the ground. He adjusted his coil so that the current flowed into the soil and returned through the air. The planet became a conductor. Every outlet, every metal beam, every water pipe is connected to a huge electrical network buried under the floor. A tuned pulse can find these pathways. When the resonator emitted a surge, it didn't just discharge into the air, it connected with the building's grounding system. The current flowed through pipes, fittings, even through the concrete itself. Any nearby metal became an antenna, metal cabinets, ventilation ducts, metal shelves that caught the discharge. The laboratory momentarily turned into part of a circuit. Imagine the wiring of your house as a huge metallic web. Strike the right note, and the entire web will hum. This hum can be powerful. Now add a twist related to the year 2020. Artificial intelligence in the system. The team did not conduct frequency measurements manually. They used an automated testing platform. Machine learning guided the process. The artificial intelligence model scanned coils, built impedance curves, and found optimal transmission points. This happened in seconds. It could take a human technician several hours to tune the resonance peak. The artificial intelligence found it instantly. It was searching for maximum energy binding. This was its job, and it did it excellently. The algorithm selected 700 kilohertz and sent a signal exactly in that range. The resonator became blocked. The voltage began to rise exponentially. A surge occurred before anyone could react. The system was not affected by anything supernatural. It was optimized. The artificial intelligence detected a dangerous frequency and hit the target precisely. No malice, only mathematics. This also explains the evacuation. High-voltage sensors detect the ionization cascade. Protocols trigger automatically. The building security system does not wait for human decisions. It clears the space. The title remains unchanged. The old Tesla device activated. The laboratory was quickly evacuated. The reason lies in resonance and modern tools, not in mysticism or physics. If it happened once, what else might awaken when artificial intelligence turns to the past? The fact is that Tesla's ideas have not disappeared. They have evolved. Defense laboratories are currently testing directed energy systems, high-powered microwave beams, particle accelerators designed to disable electronics from a distance. DARPA funds wireless energy transmission. The goal is to charge drones in flight, without landing, without wires, only directed microwave transmission over distances of kilometers. NASA explores solar energy from space. Huge orbital arrays transmitting energy to Earth using phased microwave transmitters, the same principle Tesla envisioned at Wardenclyffe in 1901. The Air Force uses active denial systems, millimeter wave beams that heat the skin without penetrating it. Crowd control through directed electromagnetic energy. These are not marginal projects. They are funded programs with published results, and each of them is based on resonance, tuned frequencies, optimized coupling. The physics that Tesla demonstrated over 100 years ago. The old coils show physics, not fantasy. They prove that the concept works. Modern systems simply add precision, control, and scale. But there is one safety nuance that many overlook. Old parts can be dangerous. Oil capacitors age, insulation cracks. One discharge can turn a relic into a grenade. This is why protocols are so important. High-voltage arcs create ozone and nitrogen oxides. Inhaling too much can burn your lungs. Ozone oxidizes tissues. Nitrogen oxides form acid in the airways. Unforeseen arcs can ignite paper, wood, insulation. A discharge of 2 million volts carries enough energy to vaporize copper. Molten metal flies apart. Fires ignite quickly. Old dielectrics may contain polychlorinated biphenyls, toxic compounds banned since the 1970s. When old capacitors overheat, they release vapors. These vapors cause neurological damage. Evacuation is not theatrical. It is a standard procedure when the sensors are triggered. It protects the lungs, eyes, and equipment. The safety system makes no exceptions. The team followed protocol. Alarm signals went off. Everyone began to move. The building was locked down until air quality returned to safe levels. So if the spike wasn't an accident, what do you think caused it? Tell us in the comments before we reveal a shocking possibility. This is not sabotage, not a joke, but something more subtle. Something that happens more often than laboratories acknowledge. Some coils behave like passive receivers. They do not need energy to activate. They need the right frequency passing nearby. Tesla resonators were created to interact with remote transmitters. This is the main idea. Powerful local radio frequency fields can transmit energy to them. Cell towers, Wi-Fi routers, radar installations, and even amateur radio operators working at high power all play their role. New York has thousands of transmitters. FM radio frequencies from 80 to 100 megahertz. cellular bands from 600 megahertz to 6 gigahertz. Emergency services use very high frequency and ultra high frequency ranges. A coil tuned to 700 kilohertz is at the center of the AM range. Strong signals from nearby transmitters can induce current. Not too much, but enough. A freed wire or probe can complete the circuit. The analyzer's input cable became an antenna, capturing the surrounding radio frequency energy and transmitting it directly to the resonator. The coil accumulated charge. When the circuit closed, the stored energy discharged instantly. The result looks like self-expression, but it is not. It is induction. It is a connection. Radio waves do what they always do. They find resonating structures and fill them with energy. A hidden connection can turn a silent sculpture into an active source of energy. This is the real shock. There is another aspect to consider. The hidden connection is important not only for one laboratory or one coil. This is relevant now, as artificial intelligence will soon be testing more old prototypes. Universities hold many forgotten devices, industrial relics, defense prototypes from the Cold War, early radio transmitters, particle accelerators from the 50s, all stored in warehouses. The teams are cataloging, scanning, and mapping their properties using modern tools. These are the same tools that triggered a surge in the resonator's work. Expect new discoveries. Expect unexpected surges. Some of them will be harmless. Others may harm researchers or destroy irreplaceable artifacts. Museums need new protocols for working with high voltage. Laboratories do too. Auction houses dealing with hereditary collections also. A brass coil that looks like a sculpture may turn out to be an active bomb waiting for the wrong frequency. But there is a positive aspect. Engineers can learn from the designs of the past. Tesla built coils by hand. No software for simulations, no finite element analysis, only intuition and experiments. His resonators achieve such coupling coefficients that modern designers struggle with. The study of these devices reveals secrets, tricks, winding schemes, insulation methods, grounding strategies that work better than modern standards. This could lead to safer wireless charging, better energy transfer for drones and satellites, and more efficient medical devices. Old equipment holds answers if deciphered correctly. A resonator is like a swing. Small pushes in the right rhythm can create a big effect. This is exactly what happened. The right rhythm found very old swings. Let's decode the physics in simple terms. A Tesla coil consists of two loops, primary and secondary. The primary is a thick wire wrapped in several tight coils. The secondary is a thin wire wound thousands of times in a tall spiral. Each loop has its own natural rhythm. This rhythm is called resonance, like the tuning of a pendulum that sounds at a specific note. When you pass electricity through the primary coil at its natural rhythm, magnetic fields arise. These impulses reach the secondary coil. If the secondary coil is synchronized with this rhythm, it responds. The voltage rapidly increases. You can imagine how you push a child on a swing. Small pushes at the right moment help to go higher, while the wrong rhythm wastes energy. The right rhythm builds momentum. The analyzer pumped the primary coil with precise rhythm. The secondary coil responded. The voltage doubled, then doubled, again and again. Within milliseconds, the coil reached 2 million volts. Ground networks can amplify this ascent, acting like echo chambers. The energy reflects back into the circuit instead of dissipating. The impulse becomes stronger. Modern devices provide cleaner and more powerful pulses. Without spark discharges and mechanical vibrations, only pure sine waves captured at peak resonance. AI-based tools quickly find the perfect rhythm, faster than a human can. The algorithm tested thousands of frequencies in seconds. It found the one that would strike. A harmless oscillation crossed a dangerous threshold. The reel could not distinguish between the test signal and the attack. It simply reacted to the rhythm. So, how do we prevent this next time? Laboratories and museums need a checklist. Simple rules that will prevent surges without blocking research. Mark outdated coils as potential receivers, not just transmitters. They can capture energy from the environment even when turned off. Isolate the grounds before any fluctuation. Disconnect the coil from the building's grounding. Use isolated testing stands. Break the communication paths. First, use sources with limited current. Start with milliamp sources. Measure the response. Increase the power only if the device remains stable. Keep the probes away from the primary coils. Even a free test conductor near the entrance coil can induce. Position matters. Add radio frequency screens during cataloging, Faraday cages, or grounded metal screens. Block external transmissions from reaching the device. Practice evacuation drills for high voltage events. Everyone should know the exits. alarm sounds, and the location of distribution panels. These steps require minimal costs. They save lives and artifacts, allowing researchers to study the past without the risk of the next surge. We have not yet finished with Tesla. We can respect the past while moving forward. Old techniques combined with new tools can safely open access to the best technologies in energy. Because this is where imagination meets engineering. Some researchers study resonant connections with the Earth, not for broadcasting, but for point-to-point energy transmission underground. Submarines use extremely low frequencies for communication through seawater. These signals travel through the Earth's crust. Resonant coils tuned to the same frequencies can transmit energy in the same way. Others are testing long-range energy transmission for flights. Drones that never land. Aircraft charging in the air using phased microwave arrays on the ground. Artificial intelligence can determine safe, resonant windows in real time. Frequencies are found that transmit energy without creating dangerous arcs or interference. The goal is efficiency. More energy for each watt transmitted. Safe energy transmission. Medical implants are charged wirelessly without the need for surgical intervention. Electric vehicles receive power while in motion. No outlets, no degrading batteries. An idea that has existed for a century may find modern application. Tesla envisioned wireless energy transmission when electricity was just beginning to develop. Now we have the materials, control systems, and computing power to realize it. Let's close the loop. An antique resonator is working in a modern laboratory space, not because of ghosts, not because of hidden batteries or a perpetual engine. Resonance made it possible. Binding made it dangerous. Artificial intelligence accelerated the process. The security systems worked as intended. The sensors detected ionization. The alarm signals activated. The building was evacuated. No one was harmed. The protocols saved the situation. This case shows why old developments still matter. They demonstrate principles that we continue to study. They reveal what is possible when physics perfectly aligns. The past can inspire the future with the right approach. We do not need to repeat Tesla's mistakes, but we can rely on his ideas. This moment was not a myth. It was a warning and a valuable map. When the old rhythm meets new energy, expect sparks.